Here is an example when we consider the light color sampling by our retinal cones on the light spectrum. We humans have 3 types of cones, each most sensitive to red, green, or blue light. This plot shows the sensitivities of each type of cones to different light of different wavelengths, between 400 and 700 nanometers for the range of visible light. You can see that red and green cones actually are very similar in terms of the sensitivity curves. So this red curve is for the red cone, and the green curve is for the green cone, and the blue curve is for the cone more sensitive to the blue light. Okay, and you can ask whether efficient coding principle can help us to understand why these 3 cones are made this way by nature. Okay, for example, why is this green cone most sensitive to, let's say, 540 nanometers? Why isn't this green curve slightly shifted towards that direction so that the peak sensitivity is more towards the shorter wavelength, right? And so it turns out that we can indeed do that to understand this from efficient coding principle. So let's formulate it this way, yeah? Okay, in this case, the signal input really is the surface reflectance function of any surface of an object. Okay, so for instance, a red object reflects more red light and green object reflects green light. So any surface reflects light depending on the wavelength of the light. So it's a function of a wavelength for its reflectance. Okay, wavelength lambda. And O is the responses of the 3 types of cones. And so it's a 3-dimensional vector for response OR for the green cone, red cone, green cone, and blue cone. Okay, and given sunlight, let's say the sunlight is also, it's a function of light wavelengths, have different intensity for different wavelengths of light. And so then the light reflected from an object is this sunlight times the reflectance of the object surface, and that's a function of lambda again. Now let's also describe our cones by its sensitivity function. Let's say this function is function of lambda, and we approximately treat all these 3 cones having the same shape of the function f. And the only difference between these 3 cones is, let's say, where they peak. Okay, let's use lambda I to describe where they peak. So lambda I is red and green and blue. So for the red cones, the lambda I is long. For the red cone is lambda I is long, green cone slightly shorter lambda, and blue cone even shorter lambda. Okay, let's treat it this way. And so for each cone, you can then get its response as its sensitivity to light times the actually reflected light from the surface, and you integrate over all the wavelengths to get its response, plus the encoding noise. Okay, and then the encoding K becomes the choice of these 3 peak lambda values. Okay, so 3 peak lambda. For each set of 3 peak lambda, you can calculate what should be the mutual information between the response O from the cones and surface reflectance. Okay, and so you can calculate that, and then you find what should be the 3 peak lambda such that this mutual information is maximized, and that 3 lambda should be how nature designed it. Yeah, and so therefore, given in nature the probability distribution of all the object surfaces and how they reflect light, and given the property of the noise, and if you are given with what the sunlight is made of, then you can calculate this mutual information as a function of the 3 lambdas, and then choose the 3 lambdas to maximize it. And it turns out that indeed this can be used to understand how why our visual systems have this kind of a cone design.